Before we explore the possibilities, understand the foundations. The concept of time travel isn't just a product of imaginative sci-fi worlds, it finds its roots in the groundbreaking work of Albert Einstein. His theory of relativity turned our understanding of time on its head. Contrary to our everyday experiences, time, as Einstein proposed, is not a constant. It's a dynamic entity, bending and twisting under the influence of gravity and velocity. Imagine a giant cosmic trampoline with a bowling ball in the middle. This ball represents a massive celestial body, say a planet or a star. The way the ball causes the trampoline to dip, that's analogous to gravity causing space-time to curve. Now let's roll a marble across the trampoline. The marble's path will curve as it rolls towards the bowling ball, mimicking how a planet orbits a star. This is the essence of Einstein's general theory of relativity. Gravity is the curvature of space-time caused by mass. Now here's where it gets really interesting. According to Einstein's special theory of relativity, the faster you move, the slower time passes. This is called time dilation. Picture two identical clocks. One remains stationary, while the other is zooming around at near light speed. When the moving clock returns, it will have recorded less time than the stationary one. In essence, the moving clock traveled into the future. So, does that mean if you run fast enough, you could slow down time? Well, in theory, yes, but you'd need to run really, really fast. We're talking about speeds close to the speed of light, which, for the record, is about 670 million miles per hour. Not exactly achievable with the latest running shoes. That's the first glimpse into the time-traveling rabbit hole. The mere thought that time isn't a fixed, unchanging entity, but a dynamic, malleable dimension that can be influenced. That's a concept that opens up a universe of possibilities. And it's just the beginning of our journey into the world of time travel. Enter the concept of wormholes, cosmic shortcuts that could potentially connect distant points in space and time. These are not your typical tunnels, but rather hypothetical structures within the fabric of space-time itself. Picture a sheet of paper folded in half, with a hole punched through the two layers. That's a rudimentary way to visualize a wormhole. Wormholes are a fascinating prediction that springs from Einstein's theory of general relativity. According to his equations, the fabric of space-time can be bent and twisted, and wormholes are a result of such extreme distortions. They are essentially bridges connecting two distinct points in space and time, potentially light years apart. Now, if you're wondering whether wormholes could be our ticket to time travel, you're not alone. Scientists have been pondering this possibility for decades. Theoretical physicist Kip Thorne even suggested that if wormholes exist and can be stabilized, they could serve as time machines. Yes, you heard it right, time machines. But before you pack your bags for a time-traveling adventure, there's a catch. Stabilizing a wormhole would require a type of matter with negative energy density, something that's not known to exist in our universe. And even if it did, creating a wormhole would need an extraordinary amount of energy, on a scale that's currently beyond our reach. Despite these challenges, the concept of wormholes remains a tantalizing possibility in our quest to understand the nature of time and space. They represent a bridge not just between different points in space, but also between our current understanding and new unexplored realms of physics. Wormholes, if they exist, could be the cosmic subway systems that allow us to leap across the vast expanse of the universe. While we may not be ready to jump into a wormhole just yet, the very idea challenges us to push the boundaries of our knowledge and dream of possibilities that seem straight out of science fiction. Ever heard of time dilation? This fascinating phenomenon is a cornerstone of Einstein's theory of relativity, and it's all about speed and time. Picture this. You're on a spaceship traveling close to the speed of light, and as you accelerate, something strange starts to happen. The clock on your spaceship seems to be ticking normally, but if you could somehow peek at a clock back on Earth, you'd see it racing ahead. This isn't some fanciful science fiction. It's a reality proven by experiments with fast-moving particles. When these particles traveling near the speed of light are observed, their internal processes seem to slow down. They decay less rapidly, effectively living longer than their stationary counterparts. This is time dilation in action. The faster an object moves, the slower time passes for it. Now let's bring this concept back to our imaginary spaceship. Suppose you're an astronaut on a mission to a distant star. You're traveling so fast that, upon your return to Earth, you might find that while you've aged only a few years, decades have passed back home. Your journey into the future wasn't through a wormhole or a time machine, but simply a result of traveling really, really fast. But there's a catch. To achieve such significant time dilation, you'd need to be traveling unbelievably close to the speed of light. And currently, our fastest spacecraft are nowhere near that speed. Plus, even if we could reach such speeds, there are other challenges to consider, like the energy required and the effects of space-time distortions. So, time dilation presents us with a tantalizing glimpse into the potential for time travel, or at least time manipulation. And while we're not packing for time-traveling journeys just yet, the implications are profound. The faster you go, the slower time passes. Astronauts on a super-fast journey might come back to find Earth's clocks ticking faster than their own. Now, let's confront the famous grandfather paradox. Imagine, if you will, stepping into a time machine and journeying back to a time before your grandparents even met. What if, in the course of your travels, you inadvertently interfere with their meeting, thus preventing your own birth? This is the grandfather paradox, a staple of time travel lore that throws a wrench into the very concept of altering past events. It's a theoretical logjam, a puzzle that challenges our understanding of time and causality. This paradox raises profound questions about the nature of time and causality. If you prevent your own existence, then you wouldn't have been able to travel back in time in the first place. It's a loop, a cycle that cannot logically resolve itself. The question then becomes, can we alter the past without creating such paradoxes? But what if the universe has a way around this? Some theories suggest an answer might lie in the concept of parallel universes or the multiverse. Instead of altering our own timeline, perhaps what we're really doing is creating or shifting to a new parallel timeline. This new timeline is almost identical to our own, but with the changes we've made. In this way, you could prevent your grandparents from meeting without erasing your own existence. You would simply exist in a different universe where you were never born. This is the concept of the multiverse, a potentially infinite collection of parallel universes where every possible outcome of every event coexists. This idea of parallel universes isn't just a convenient workaround for time travel paradoxes. It's a serious, albeit speculative, area of study in physics, with theories like quantum mechanics suggesting that parallel universes could indeed exist. So, could the grandfather paradox be solved by the existence of parallel universes? Perhaps. But as we delve deeper into the mysteries of time travel, remember that these concepts are theoretical, and our understanding of time, causality, and the universe is constantly evolving. Parallel universes might be where every possible outcome coexists. While time travel is mostly in the realm of science fiction, scientists are exploring its potential real-world applications. Time travel isn't just about hopping into a DeLorean and zipping back to the past or future. It's about understanding the fundamental laws of our universe. Studying time travel theories could lead us to a better understanding of the early universe. The Big Bang Theory suggests our universe began as a singularity, a point of infinite density and gravity. If we could travel back in time, we could potentially observe this singularity and learn more about how our universe evolved. Time travel research also has implications for our daily lives. Super-accurate clocks, for instance, are a direct result of understanding time dilation. These clocks are vital for systems we rely on every day, such as the global positioning system. GPS satellites are moving quickly relative to the Earth's surface, and thus experience time slightly slower. To keep the system accurate, the clocks on these satellites must account for this time dilation. However, the journey to unlocking the secrets of time travel is not without its challenges. One of the biggest is the need for vast amounts of energy. Creating a wormhole, for instance, would require energy equivalent to the mass of a star. That's a tall order for our current technology. Furthermore, the very fabric of the universe itself presents a challenge. The universe is a complex and mysterious place. We're still trying to understand dark matter, dark energy, and the true nature of gravity. Each of these could have significant implications for time travel. In essence, time travel research is a journey of discovery, pushing the boundaries of our knowledge and technology. It's a quest that takes us into the heart of the universe and the nature of time itself. The mysterious nature of the universe makes time travel a daunting challenge. But as we've seen throughout history, tackling daunting challenges often leads to incredible discoveries. As we wrap up our journey through the mysteries of time, remember that time travel is still a fascinating concept filled with paradoxes and possibilities. We've plunged into the depths of Einstein's relativity, explored the cosmic shortcuts of wormholes, and grappled with the mind-bending effects of time dilation. We've faced the enigmatic grandfather paradox and considered the tantalizing prospect of parallel universes. And we've glimpsed at the real-world implications and challenges posed by time travel, from studying the early universe to refining our GPS systems. But our journey is far from over. Each discovery, each paradox, each theoretical leap forward brings us closer to understanding and perhaps one day mastering the mysteries of time. And as we traverse this uncharted frontier, we remember that the thrill of the journey lies not just in the destination, but in the exploration itself. The journey to unlock the secrets of time travel continues. Until next time, time travelers.